Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back. Today's lesson will be on metamorphic rocks. If you recall, we talked about three major classes of rocks. One was volcanic rock, then we talked about sedimentary rocks, and today we are going to wrap up the discussion on rocks by talking about the origin and origin, engineering issues and uses involving metamorphic rock masses and metamorphic rock terrains. Okay, before we get on with today's lesson, we are going to look at the questions that were given to you as part of the previous lesson. These are the questions. The first one was that with increased temperature, pressure and pH, formation of limestone is accelerated or impeded. Okay. Now, in order to understand that, we have to consider the chemical reactions involved in the formation of limestone. The basic chemical reactions are like this. Let's consider a solution, aqueous solution of calcium carbonate, how that actually changes. So, we started with aqueous solution of calcium carbonate, and that is going to be reacted upon by, we have got another mistake here. That is going to be reacted upon by carbonic acid, and then what we are going to end up with in this process is release of calcium ion and this another ion. Both of these things are going to be in aqueous phase again. Now, this carbonic acid actually is going to come from dissolution of carbon dioxide in water, and the reaction involved in that process goes like this. So, this carbonic acid ends up reacting with calcium carbonate. Now, what happens actually? Let's consider let's consider reaction 2. Let's consider reaction 2. I mean, how reaction 2, the forward rate of reaction 2 is actually accentuated. and then we will look at what is the impact of that particular rate on the precipitation or dissolution of calcium carbonate. Now, the forward reaction of dissolution of carbon dioxide in water and formation of carbonic acid, that is actually accentuated by decrease in temperature. So, if temperature goes down, then the forward reaction is actually accentuated. Then if pressure goes up, then more and more carbon dioxide gets dissolved in water, and that leads to the formation of more and more carbonic acid. So, these are the two factors that leads to increased dissolution of CO2 and thereby increased H2CO3 formation. Now, since H2CO3 formation is going to actually trigger the forward reaction of dissolution of calcium carbonate, the forward reaction of chemical reaction 1 also is going to be accentuated, catalyzed by this particular process. So, this will also lead to an increase in the rate of dissolution of calcium carbonate. And the reverse is true if we and the reverse is also true. In other words, if we actually impede generation of carbonic acid by increase of temperature or decrease of pressure, then that is going to lead to the precipitation of calcium carbonate. So, what is going to happen then is, if we actually increase temperature and decrease pressure, then we are going to get more and more limestone, and if we reverse these two influencing factors, then limestone is going to get dissolved in carbonic acid. Now, we also talked about pH. Now, you notice that the reaction, the forward reaction, actually the forward reaction of chemical reaction 1, actually that is that the rate of that increases as the pH goes down. So, if we actually increase pH, then that also is going to catalyze precipitation of limestone. So, basically these are the major factors that affect the precipitation of limestone or calcite mineral in the form of limestone. And the second question that I asked was, seawater is considered to be a necessary ingredient in dolomite formation. Why that is so? Now, to understand that, again we have to look at the chemical process involved in the formation of dolomite. Now, what happens there is this: we have got one reaction in which we end up in dissolution of calcium carbonate, like what we had before, and then what happens is this. So, this one here is your dolomite, and basically these chemical reactions are clubbed together and are given the name dolomitization. Now, the forward reaction for chemical reaction 2, forward rate of 2 is catalyzed by a few factors. The major ones are like elevated availability of magnesium as opposed to calcium ions, then elevated temperature as well, and actually availability of calcium carbonate in the aragonite form rather than in the calcite form, which we actually looked at earlier. Actually what I am trying to say here is calcite and aragonite, they are polymorphs. So, what we need in order to catalyze the formation of dolomite is availability of aragonite rather than calcite. Now, all these things, particularly this one is met when seawater gets mixed up with fresh water, fresh groundwater, and the and seawater itself acts as a source of magnesium ions. So, that is the reason why presence of seawater actually is considered a necessary ingredient for the formation of dolomite. Okay. Reverting back to the third question, I asked you to explain the terms ripple marks and gradational bedding, and these things were discussed in the last lesson itself. So, ripple marks are the relict forms of wave actions that are readily visible in the texture of sedimentary rock, as is shown in this sketch here. So, this is the appearance of ripple marks in a sedimentary rock structure. Gradational bedding, on the other hand, is going to be like this. You imagine that sedimentary rocks are often bedded in this form, and each of these beds are going to be become finer upward or finer downward as far as the particle size of the composing mineral grains are concerned. So, in this case what I have shown is that the particle size is decreasing as you move upward, and the same kind of feature is going to be repeated in other beds as well. So, this is called a gradational bedding. Okay. All right. So, that kind of takes care of all the questions that were given to you in the previous class, and now we hop on to today's lesson. So, what we are going to learn from this particular lesson, we are going to look at the agents of metamorphism, the basic causes that lead to the development of metamorphic rocks. Then we are going to classify metamorphic rocks, look at the grades of metamorphic rocks, and we are going to consider basic engineering issues that are involved with metamorphic rocks and economic uses of metamorphic rocks. Okay, what is meant by metamorphic rock? That is the first question that comes into mind. Metamorphosis, you know, you may have encountered this term elsewhere, and what is meant by that is a process of change. Now, here what happens is what is meant by metamorphic rock is it essentially signifies the fact that these rocks develop by changing of pre-existing rocks. These pre-existing rocks are often called protoliths, and they could be composed of sedimentary or igneous parent rocks, or in fact they could be even metamorphic rocks, pre-existing metamorphic rocks. What causes metamorphism? Metamorphism can be triggered typically by increased pressure, temperature and fluid action. We will see the details of these things as we continue with this presentation. Now, the effect of metamorphism leads to textural and mineralogical changes of the composition of the rock. Although in some cases what is going to happen, you will see that the relict forms of the pre-existing rock is maintained. So, metamorphic rocks then originate from the action of different agents of metamorphism on pre-existing rocks of primarily all the three varieties, i.e. Igneous rocks, sedimentary rocks and metamorphic rocks. So, what are the agents that trigger metamorphism? The first one is temperature change, and what is important here is the temperature gradient, because you can imagine that as you go down deeper from the surface of the earth, then the temperature actually increases at a rate of approximately 35 degrees Celsius per kilometer depth. So, with deep burial, a pre-existing rock mass, deep burial because of something, because of tectonic activity or because of mountain building or because of any other geologic process, the pre-existing rock mass is going to be subjected to an elevated level of temperature. Magma intrusion of partially molten rock forming materials, that also is going to elevate the temperature of the rock within the rock that surrounds the intruding magma. Then another agent that actually triggers metamorphism is pressure change. As it happened in case of temperature with burial, pre-existing rock will be subjected to an elevated level of pressure, because it has to withstand the pressure of the rock or other materials that actually comes on top of it. Pressure change could also be directional, and this particular situation happens when in the continental margin, where one particular tectonic plate collides with another plate, and as a result there are several different regimes of compressional and tensile stresses develop in the lateral direction. Then chemical change could also be an agent of metamorphism, and chemical change is often triggered by the temperature change and pressure change, or it could be because of dissolution in of rock minerals. Okay. Now, second thing what is important here is the grades of metamorphism. How do we classify grades of metamorphism? Now, in order to understand that, what we need to understand is what basically happens because of metamorphism. Now, primarily what happens because of metamorphism is the minerals within the pre-existing rock, if they are hydrous minerals, they are going to lose increasing proportion of water within the mineral structure, and also they are going to lose gases such as carbon dioxide. So, basically metamorphism involves reduction of hydrous mineral percentage within the rock mass, and also there will be reduction of carbon dioxide within the mineral structure. So, that actually leads to the change of it actually changes one mineral to another. Now, these two processes are triggered by primarily by increases of temperature and pressure. So, as the process matures, in order to have a mature metamorphic process, we need to elevate the temperature as well as we need to elevate the pressure. So, this particular chart here shows a plot where we look at different metamorphic grades. So, when there is not much of change of temperature and pressure, the processes involved in that case is diagenesis. We know what is meant by that term from our previous presentations, and then we get into the zone where what is known as low grade metamorphism, which actually takes place in the temperature range maybe 200 to 300 degrees Celsius, and pressure range of between 300 megapascals to about 600 megapascals. If we increase the temperature further and or increase the pressure further, then we get into intermediate grade of metamorphic rocks, and the temperature range for that is between 300 and 500 degrees Celsius typically, and the pressure at which intermediate metamorphic rocks develop, that actually varies typically between 600 and about 1000 megapascals. If the temperature and pressure increases further, then we are going to get high grade metamorphic rocks, and these rocks are going to be going to contain least percentage of hydrous minerals such as different varieties of mica, and the ranges of temperature and pressure for high grade metamorphism is shown on the plot there. The temperature could vary anywhere between say 500 and say typically 800 to 900 degrees Celsius, and the pressure range is typically more than 1000 megapascals. And if you increase the temperature further and or increase the pressure further, you are going to end up with melting the rock mineral partially. So, what is happening here on this chart is that as we go down from top left to bottom right, we are losing more and more hydrous minerals, and we are going to also lose gases such as carbon dioxide. So, these are the two major features of these processes, and also we will see later that in this particular direction we will start typically from clay minerals, there may be some quartz and other stable minerals also in the rocks that we begin with, but these clay minerals actually are going to be going to evolve into chlorites. Then we are going to start getting more and more micas, and then we are going to start getting more and more there will be quartz actually in quartz and feldspar in all the cases, feldspars. And here also we will get quartz and feldspars, and we will get more and more minerals of other varieties as we proceed to the bottom right, such as we are going to start getting amphiboles and pyroxenes as we move down to the right. Okay, so that actually in a nutshell gives you the what is meant by grades of metamorphism. All right. Now, there are different types of metamorphic rocks or metamorphism. The process of metamorphism, depending on what factor triggers the process, there will be several different types of metamorphism, and those are listed here. The first one is called contact metamorphism. In this case, metamorphism is triggered by an intruding mass of molten magma. Then we can have regional metamorphism, and this particular type of metamorphism is triggered by a large scale geologic process such as tectonic collision or other types of tectonic activities, mountain building process, and so on and so forth. The third type of metamorphism is called cataclystic metamorphism, and this type of metamorphism is triggered within near the vicinity of a fault. We know what is meant by fault from one of the earlier presentations. and also there are other types of more rare forms of metamorphism, such as hydrothermal metamorphism. Actually, I would not call hydrothermal metamorphism as a rare one, but this is actually triggered near the divergent boundaries. We will see actually what is meant by divergent boundaries when we get into plate tectonics later on. These are essentially undersea vents from which molten magma comes to the surface near at the sea floor, leading to the formation of basaltic rocks. Hydrothermal metamorphism is triggered basically by convecting water at elevated temperature near surface actually. And finally, we could also trigger metamorphism because of very heavy impact, such as those encountered during the impact of meteorites. So what I wanted to suggest here is that this type of metamorphism is quite rare, whereas these two are relatively rare and these two are quite widespread actually, relatively speaking. What we will get into the details of each one of these things in the next little bit, and we will start with contact metamorphism. So what drives contact metamorphism? Contact metamorphism is driven by triggered by the fact that a large mass of molten magma intrudes into pre-existing rock mass. That could be sedimentary rock, or that could be other types of chemically formed rocks, or volcanic rock, or all kinds of rocks. In those, if it is intruded by molten magma, then what happens? The rock mass that surrounds the molten magma is going to be subjected to elevated level of temperature, not so much an increased pressure, and that temperature gradient actually triggers chemical changes, chemical and mineralogical changes, and that is the cause of contact metamorphism. These things, this type of metamorphism typically takes place at shallow depths, because at shallow depths only you are going to get a large temperature gradient. What we mean by temperature gradient is that the rate of change of temperature spatially as we move from the surface of the intruding magma to the surrounding rock, away from the intruding magma. Now, what happens actually as we go to deeper layers, then the surrounding rock around intruding magma is going to be also at an elevated temperature. As a result, we are going to have a larger rock mass around the intruding magma at a relatively larger temperature, and the temperature gradient as a result is going to decrease quite a bit as we go down deeper. Now, what we also have in this case is the pressure gradient is relatively small, and as a result this particular type of metamorphism gives rise to rocks that are not foliated or layered. What we mean by foliation is essentially the foliated rocks, they are composed of interlayered structure, as we will see in the next little bit. Now, there are a couple of definitions in this connection. The intruding rock mass, the rock that surrounds the intruding rock mass where metamorphism is taking place, that particular layer around the intruding magma is called aureole. And examples of rocks that arise because of contact metamorphism include hornfels primarily, and you could also get quartzite and marble. Now, we want to have a look at different grades of contact metamorphism, and as we have stated, as we have learnt earlier, that pressure increase in this case is going to be relatively modest. So, we are going to look at depths typically less than 10 kilometers and pressures typically less than say 300 MPa, and in this case we are considering the grades of metamorphism that arises because of metamorphism of pellitic, quartz feldspar and mafic rocks. The term pellitic is new to you actually, and what is meant by that is rocks that are composed of primarily of clay minerals that actually arises from diagenesis and cementation of clay layers of clay. Examples of this type of rock includes clay stone, shale and so on and so forth, and slates also, although slate is a little bit farther down on the grade of metamorphism compared to shale rock. Now, we can see the different types of metamorphic rock that arises because of contact metamorphism, and that is shown here on this particular chart. This is actually a section of the plot that we have already seen, and here what we are interested is the range shown as a range that is shown as yellow shade. So, what we are looking at is this particular area, this particular range of pressure and temperature, and here, as is evident, we begin typically from rocks that contain a large proportion of clay minerals. Then we move on to a particular class of rock which is known as the albite epidote hornfels facies, which is to the left, which is near the left end of the range of pressure temperature that we are considering here, that contains predominantly albite mineral, quartz, chlorite and calcite. Then we move on to the hornblende hornfels facies. In this case, we have got primarily chlorite, we have got primarily quartz, plagioclase, muscovite and biotite mica and calcite. And what you should notice here is that from these facies, chlorite and epidote minerals are going to be absent typically, and then as the grades of metamorphic rock becomes higher, then we are going to get into pyroxene hornfels, which contain a large proportion of pyroxene minerals. What you are going to get here is absence of muscovite, hornblende and calcite, and finally at the highest grade, where we are very near to the intruding magma, you end up with a class of rock which is called sanidinite facies, and here you are going to have a total absence of hydrous minerals such as micas and abundance of pyroxene minerals. In other words, you must have noticed, if you recall from what we have said when we were talking about chemical composition of silicate minerals. The pyroxene minerals are essentially single chain minerals. So, as the grade of metamorphism matures, what we are getting is a reduction of the proportion of hydrous minerals, a reduction of double chain minerals, and an increase of single chain minerals. So, that is the major process that you should take a notice here. Now, contact metamorphism also leads to the formation of another type of another class of metamorphic rocks, which originate when magma intrudes into pre-existing carbonate rocks such as limestone and dolostone. Now, the type of terrain that actually develops in this process is called skarns. Now, here what happens, this particular in this particular case, we start from calcite brucite minerals. If you recall what is meant by brucite from your chemistry class, or from the discussion what we have, what you may already know actually this one. So, what we mean by brucite is essentially this particular chemical. So, here we start with calcite brucite. Calcite, as you know already, that it is simply calcium carbonate, and then at the lowest grade of metamorphism, we get marbles in this case. Essentially, calcite, this arises because of recrystallization of calcite and brucite, and then we, as the metamorphic grade increases, then we will get minerals such as sparite, calcite is also present. Then we will end up with minerals that has a larger proportion of pyroxene minerals such as diopside. So, essentially what, and finally, as the grade, as the metamorphism matures even more, then we are going to get garnets and quartz to an increasing extent. And here also you should know that as the metamorphic grade increases, then we also get more and more mineral ores, such as ores of gold and ilmenite, tungsten, and so on and so forth. So, the metamorphic rock feces, which is near the contact of the intruding magma and the surrounding pre-existing rock, are often rich sources of those kind of mineral ores, and we will see this thing later on as we continue with this particular presentation. Okay, the second type of metamorphism that we want to consider is regional metamorphism. So, as I mentioned earlier, that this particular type of metamorphism takes place because of large geological processes such as near subduction zones or mountain buildings, and examples of rocks, metamorphic rocks, that arise because of regional metamorphism includes schists. The formation temperature in this case is between 100 and 300 degrees Celsius typically, and formation pressure is typically between 300 and 800 MPa. Amphibolite, at a larger temperature 300 to 600 degrees Celsius, 200 to 900 MPa pressure. These things actually contain double chain silicate minerals, and eclogite at much higher temperature and pressure, as is indicated at the bottom of this slide here, 200 to 700 degrees Celsius and pressure of 900 to 1200 MPa, and these things, this particular class of rock is rich in pyroxene minerals. And also another thing you should notice in this case is that as you go down, as actually the grade of metamorphism increases, the grain size, the granularity of these rocks also increase. Granularity increases with grades of metamorphism in this case. Okay. Now, this particular cartoon actually shows the grades of different metamorphic rocks that we already have discussed. So, we begin with pelagic rocks such as shales, and then we move on to phyllite, schist and gneiss with increased grade of metamorphism. And the chemical changes, as we have already discussed, involves change of clay minerals first into biotite, then double chain silicates, quartz and feldspar, and finally what happens actually because of directional pressure in this case, and that is a very major difference between regional metamorphism and contact metamorphism. This particular type of metamorphism involves application of directional pressure, and that directional pressure application leads to the segregation of mafic and felsic minerals, leading often to a foliated structure like what is seen on the pictures of phyllite, schist and gneiss. All of them are examples really of foliated rocks, or which involves which is actually a composition of plate like entities. So, this particular type of structure develops because of application of directional application of pressure, and this particular aspect was absent when we were discussing contact metamorphism. So, contact metamorphic rocks, they do not show typically foliated structure, whereas rocks that arise out of regional metamorphism processes show often foliated structures. The second, the other type of metamorphism is cataclastic metamorphism. This particular type of metamorphism occur near the fault zones, and that is because of the deformation, breakage, because of friction, and welding because of elevated heat that is generated because of the movement of fault. The processes involved here includes heat and pulverization of the rock mass, pre-existing rocks that are very near the fault zone, and the two examples, the two best examples perhaps of rocks that arise because of cataclastic metamorphism include myalonite and fault breccia. Now, there is a fundamental difference in the environment in which myalonites and fault breccia arise, and that has something to do with the depth at which the fault movement is taking place, depth below the surface. So, at greater depths the rocks are at elevated temperature and they behave in a much more ductile manner, and in this case the type of metamorphic rock that arises is myalonite, whereas fault breccia is typical of brittle failure of the rock masses around the fault zone, and this includes clasts of previously existing rock masses around the fault, and they oftentimes get welded because of heat, and that leads to the development of fault breccia. Then the other type of the next class of metamorphism is hydrothermal metamorphism, and this is really because of the interaction between the rock and hot water, and a very good source of hot water is near mid-oceanic ridges, and those hot waters near hydrothermal vents, they are called, they are rich in many different types of minerals that come out from deep underground, and this type of metamorphism is common in case of basaltic rocks which lack hydrous minerals. And an example of this class of metamorphism is an example of this type the type of rock that develops from this type of metamorphism is soapstone, which involves the chemical change of pyroxene mineral to talc mineral, and also zeolite rocks, they also to a large extent develop from hydrothermal metamorphism. Shock metamorphism, on the other hand, is caused when tremendous increase of pressure takes place, not so much of increase of temperature, tremendous increase of pressure results because say of meteorite impact or volcanic eruption, and the pressure that you are looking at is very high, on the order of 2400 MPa, and in this, if that happens, then exotic rock minerals actually develop. They are not very widely they do not occur very widely on the surface of the earth because they are unstable at ambient temperature pressure conditions. Examples of that is stishovite, which is actually a stishovite and quartzite, they are both polymorphs of quartz. If you all of them has got the chemical formula of SiO2, all of them have got chemical formula of SiO2. So SiO2 is the chemical formula of quartz, stishovite and quartzite, but you can see that the crystal structure of these three types of minerals are quite different from each other. Okay. Now, textures of sedimentary rocks. So, we have already mentioned that sedimentary rocks could be foliated or non-foliated. Foliated if they actually have got layered structure, and otherwise they are called non-foliated. Now, there are different types of foliated structure like slaty. Slaty is typically what is meant by that is it is composed of it has got slate like layers which are quite slippery when you slippery and soapy appearance or soapy feel. Then you have got phylitic texture, schistose texture and gneissic texture. So, what happens in this case actually is the grain size increases, and also the layer thickness or the foliation thickness increases. Typical grain sizes that are connected with these different types of textures are were indicated when we were talking about the textures of regional or grades of regional metamorphism. So, you should refer back to that particular slide to get a feel for what kind of grain sizes and layer thicknesses we are looking at. Non-foliated rocks, on the other hand, will not exhibit any layered structure, and examples of this type of rocks are limestone and granulite. Okay. So, this actually explains what is meant by foliated rocks, which we have already discussed. The texture is layered or foliated, and minerals have got a preferred orientation, and this arises because of directional stress application, and we have seen that examples include slate and schist. Non-foliated rocks, on the other hand, we have seen that already, that forms by recrystallization of pre-existing rock. Examples include marble and quartzite. In this case, you have got typically a structure that is composed of interlocked mineral grains. How do you name different types of metamorphic rocks? So, is explained here. Textural classification could be of three different we could do textural classification in three different ways. We could look at the mineralogy of the rock, and in this case we use two most abundant minerals as prefix to the type of texture of that particular rock. Example of that, for instance, is quartzo-feldspathic schist, which is essentially a schist, and two of the most abundant mineral in that kind of schist is quartzite and feldspars. Then we could have chemical textures, chemical textural classification. Example of that is talc magnesian schist. In some cases, classification of a metamorphic rock includes which actually do not change much from the protolith, from the texture of the protolith. In that case, we use the prefix meta to the type of rock that is that composes the protolith, and example of this type of rock is this type of classification is metagranite, in which the protolith was of granitic rock and there was slight alteration because of the metamorphic process, and what we end up with is metagranite. Engineering issues of metamorphic rocks includes schistosity and or foliation really, and that leads to anisotropic strength development and hydraulic properties, and often this type of rock exhibit creep behavior, and this actually leads to many landslide events. Economic use of metamorphic rocks. Metamorphic rocks is a very major source of rare metal ores such as tungsten and gold, which we have already discussed a little bit. It also is a rich source of precious and semi-precious stones. Schist and marble are used as building material, and gneiss is also used as building material. To summarize this lesson, we looked at the different types of metamorphism, what are the agents that causes metamorphism, lists of different types of engineering issues we considered involving metamorphic rocks. We looked at different types and grades of metamorphism, and what are the economic uses of different types of metamorphic rocks that also were considered in this lesson. We finally wrap this lesson up by a question set. The first question is, what are grades of metamorphism? The second one is, which type of metamorphism is caused by high temperature and pressure that affects a very large volume of rock, pre-existing rock. The third question that I ask is, which rock is formed by metamorphosing limestone? And the fourth one, I ask you to explain a few terms: metasomatism, aureole, and shock metamorphism, and you try to answer these questions at your leisure, and When we meet in the next lesson, I am going to provide you with the answers.